Hello, welcome to a new tutorial presented by the Hesss Law on Enthalpy Change, and the reference is Cambridge International AS A-Level by Laurie Ryan and Roger Norris. Welcome to this tutorial on Enthalpy Change, and in this tutorial we are going to have learning outcome. Our learning outcome is to explain some chemical reactions accompanied by exothermic and endothermic energy, explain the use of enthalpy change of reactions and standard condition with reference to enthalpy change of formation, combustion, hydration, solution, neutralization, atomization. Explain the use of the term bond energy, the use of term bond energy, calculate the enthalpy change experimentally using delta H is equals to negative MC delta theta, as you're going to see later, and apply the Hesss Law in order to construct simple energy cycles and carry out some calculations. Construct and interpret a reaction pathway diagram in terms of enthalpy change of reaction and activation. So let's start. So now, what is enthalpy change? Enthalpy change refers to only the energy that has either been released or absorbed due to a chemical reaction. So this energy can either be released, which is where it's called exothermic reaction, and it can be absorbed in case of endothermic reaction. Like in this case, where you have this burning with fire coming out, it's an exothermic reaction. So now we have chemical reaction where there is a release of energy is exothermic, while the entrance of energy, while the absorption of energy, a chemical reaction where absorption of energy is endothermic reaction. So now we have the surrounding. We need to know that the surrounding in this exothermic reaction, let's say that you have magnesium plus sulfuric acid to produce magnesium sulfate plus hydrogen, is this results in an energy release. In this case, the solvent is going to be the solvent, which is water, the air around the test tube is and anything which is being dipped in the test tube, like the thermometer. So these are the things that you need to visualize. In an endothermic reaction, energy is being absorbed. So an example is when you dissolve ammonium chloride. When you dissolve ammonium chloride, you have an increase in temperature of the medium. So we have other example of endothermic reaction are we have decomposition of limestone by heating. Limestone is actually calcium carbonate. So when you heat calcium carbonate to produce calcium oxide plus carbon dioxide, this is an endothermic reaction. You have also photosynthesis, in which the energy supplied by sunlight. You need to know that in photosynthesis is going to be a rise in energy, as you are going to see in biology. So enthalpy change and enthalpy profile diagram. So this is the enthalpy change and enthalpy profile diagram. So we need to visualize that what enthalpy change is the energy, the heat of the or enthalpy of the product minus enthalpy of the reactants. We need to know that in each of the reactions we have the energy of the reactants at this level and energy of products at this level. You see that there's a decrease in energy. So these days the methane and oxygen have reacted to produce carbon dioxide and water, which has a lower energy. In this case you have an exothermic reaction. And in this case, you have the heating of calcium carbonate, which is limestone, to produce calcium oxide plus carbon dioxide. See, this is an endothermic reaction. Endothermic reaction in this case, we see that it's actually an endothermic reaction, and because of increased energy from reactant to products. So now, we can now visualize the other term. In order to make sure that our study should be relevant, we have to use what is called the standard enthalpy of a reaction. So for our study to be relevant, we should use standard enthalpy of a reaction. So now, what is standard enthalpy? Standard enthalpy is actually the energy release or absorbed, and the symbol we use for standard enthalpy is delta H theta. So it's energy release or absorbed in cases it is actually the energy release or absorbed at standard condition of room temperature of 298 kelvins, pressure of 1 atmosphere in bracket 1.05 times 10 to the power 5 pascals, and lastly we have a the temperature of 290 kelvin and pressure of 1 atmosphere. So those are the conditions involved for standard enthalpy. So now we need to define other standard enthalpy, like example standard enthalpy of combustion. Standard enthalpy of combustion, in order for you to do any calculation in enthalpy change, it is best for you to first cram the different definitions of standard enthalpy. Example: standard enthalpy of combustion. Standard enthalpy of combustion is defined as the energy release, because this standard enthalpy is always the energy release. Energy release in order to burn 1 mole of substance at its corresponding state, as a corresponding chemical state to put inside oxygen. So energy release in order to burn 1 mole of substance at its corresponding state to at standard condition of 298 Kelvin and 1 atmosphere. So in this case example, you see that sulfur plus oxygen can burn, and that energy that is always released is going to be 298.8 kilojoules per mole. You see the negative here is just to show that the energy has been released. Also methane plus oxygen, see that 1 mole of this is reacting to produce an energy release of 800 negative 890.3 kilojoules per mole. So those are the points to note. Now the next thing to note again is the standard enthalpy of formation. So standard enthalpy of formation is defined as, you need to cram the definition. Standard enthalpy change of formation is defined as the energy absorbed or released, because in this case it can be absorbed or released. The energy absorbed or released in order to form the energy absorbed or released in order to form 1 mole of a substance from a corresponding element at their corresponding chemical state at 298 Kelvin, a standard temperature of 298 Kelvin, and standard pressure of 1 atmosphere. That's the definition of standard enthalpy change of formation. So you need to cram it. And lastly, you have standard enthalpy change of reaction. Delta H of theta of reaction R is defined as the energy released or absorbed in order to produce a product from the reactants at standard temperature of 290 kelvins and standard pressure of 1 atmosphere. So these are the different definitions that you have to cram. After having all these definitions in mind, you are now capable of doing the calculation by placing the different number of moles with respect to the solution and by considering their definitions. Now let's see standard enthalpy change of neutralization. The next thing is standard enthalpy change of neutralization. What's standard enthalpy change of neutralization? Standard enthalpy change of neutralization is the energy released, usually is energy released when 1 mole of is the energy released when 1 mole of hydrogen ion bind with 1 mole of hydroxide ion to produce. So when the energy released when 1 mole of hydrogen ion bind with the hydroxide ion to produce so when 1 mole of hydrogen ion bind with the hydroxide ion to produce the salt and water at standard condition of 290 Kelvin and 1 atmosphere. So these are the definition of standard enthalpy change of neutralization. And usually for strong acid strong base reaction, the standard enthalpy change of neutralization is given as negative 57.1 kilojoules per mole. But for a strong acid weak base, so for a strong acid weak base or weak acid weak strong base is usually negative 50, is going to be lesser compared to this, and this is because of a slight because the weak acid does not completely dissolve in solution producing the hydrogen ion. That's why you have a lesser standard enthalpy change in case of weak acid and strong base reaction. The next one is standard enthalpy change of solution. Standard enthalpy change of solution is the enthalpy change when 1 mole of solute is dissolved in a solvent to form an infinitely dilute solution. So you have standard enthalpy change of solution. Standard enthalpy change of solution is when you have 1 mole of substance dissolving solute dissolving in a solvent with infinite dilution. So 1 mole of substance dissolving in solvent. We also have another one which is standard enthalpy change of hydration. Standard enthalpy change of hydration is different from standard enthalpy change of solution, because for standard enthalpy change of hydration, it is inside the corresponding ions at gaseous state. It is inside the corresponding ion at gaseous state. The energy released when corresponding ion of a solute at gaseous state dissolve in an infinite solution. It dissolve in an infinite solution at standard condition of 290 Kelvin and 1 atmosphere. So these are the conditions now involved in cases of standard enthalpy change of solution. So now you have the other one, standard enthalpy change of atomization. Standard enthalpy change of atomization is the enthalpy change when 1 mole of gaseous atom is formed from its corresponding element. Example, so in this case here very well, it is standard enthalpy change for formation of 1 mole of gaseous atom from its corresponding element. That's standard enthalpy change of atomization. So 1 mole is formed here from its corresponding element. So this standard enthalpy change of atomization is going to involve half of the gaseous atom is going to be 218 kilojoules per mole. Now in case of standard enthalpy change of dissociation, it is instead the standard enthalpy change of dissociation is defined as the enthalpy change in order to produce in the enthalpy change in order to break down 1 mole of an element or gaseous molecule. For dissociation is in order to break down 1 mole of a gaseous molecule to produce its corresponding atoms. So these are the different, that's the difference between standard enthalpy change of atomization and dissociation. So atomization, standard enthalpy change of atomization, in this case for atomization you are going to have 1 year, so it's going to be standard enthalpy change of dissociation. For dissociation you are going to have 1 year, so standard enthalpy change of dissociation is going to be 1 of hydrogen year, and you are going to have the double, it's going to be a double of standard enthalpy change of atomization. So now this is standard enthalpy change of hydration. I initially said that standard enthalpy change of hydration is of anhydrous salt is enthalpy change when 1 mole of a hydrated salt is formed from 1 mole of anhydrous salt under standard condition of. So this is standard enthalpy change of hydration, another form of hydration, and this is when you have water molecule of crystallization, when it dissolves and it produces the different water molecules of crystallization. That's the standard enthalpy change of hydration. Standard enthalpy change of hydration of an anhydrous salt is the standard enthalpy change. Is the standard enthalpy change of hydration of an anhydrous. It's an enthalpy change when 1 mole of hydrated salt is formed from 1 mole of anhydrous salt under standard condition of 298 Kelvin and 1 atmosphere. So this is standard enthalpy change of hydration of anhydrous salts. So when you have water molecule of crystallization which have been added, but there is also standard enthalpy change of hydration of instead ionic components of a certain solute, and that one is the definition that I've given you later before previously. So now let's see how to measure enthalpy change via different experiments. The first one is via calorimetry. So in this case you have the reaction mixture, you have the temperature. So in this case you are going to do is in order you are going to mix the different components. Standard temperature of, in order to have the standard temperature of reaction, you are going to mix the different things here. Example, when you have a reactant, you have an acid and a base, you are going to mix the acid and base here, and when you mix them you are going to have a certain temperature that is going to give you. You know that for this you calculate the mass of the mixture and also calculate the specific heat capacity. We know that delta H, or the energy change for this reaction, is going to be equal to mc delta theta, and this theta is actually the temperature change in this medium. You take the initial temperature, the final temperature minus initial temperature, you are going to have the temperature change. So the heat is actually mc delta theta, and that heat release, you say that m is actually the mass of this mixture, which is going to be given in grams. You have a specific capacity. The specific capacity C of water is actually 4,200 joules per Kelvin per kilogram per Kelvin. Now if you convert into gram, it's going to be 4.18 joules per grams per Kelvin. So these are the different, or per degree Celsius if you want. So these are the different things that are involved here for calorimetry. And when you calculate the energy for this reaction, you can now convert to have the standard enthalpy of the reaction. So this is what is involved here. And for this other one, you have measuring via water, you have method, so calorimetry and all that. So in this case you are trying to burn propanol, and when you burn this, is going to be all the heat is going to be transferred to this water, which is going to rise in temperature, and you can measure the enthalpy change after burning this. So now the last one, the next part that you're going to, and the last one you're going to be involved here is going to be the Hesss Law. And Hesss Law is just speaking about state function. You need to know that enthalpy change is a state function. That is, it is just like gravitational energy. Example: if you are upstairs, you are, let's say, at 3 floors from the ground, 3 floors from the ground, and now go downstairs to the first floor, and then you go upstairs again to the 5th floor, and then you go again down to the 0th floor, and then you go up to the 10th floor, and then you come back to the 3rd floor. So let's say that you have moved all this, you have done all this movement. What is going to be your gravitational potential energy at the beginning and the gravitational potential energy at the end? You need to know that at the beginning you are the 3rd floor, and at the end you have moved all through the building, but you still ended at 3rd floor. You see that the 3rd floor at the beginning is the same as the 3rd floor at the end, and you need to know that gravitational potential energy is a state function. That is why you have the same gravitational potential energy initially and later, no matter which direction you have taken from the beginning to the end. So this is how Hess's law can be applied for enthalpy changes. No matter in which path you are being involved, you are going to have the Hess's law is going to be only the enthalpy change of reaction is going to be only dictated by the products and the reactants. So now let's state Hess's law from the state function of enthalpy change. It states that total enthalpy change of reaction is independent of the route by which a chemical reaction takes place, but only on the reactants and the products. So at the initial, that is like gravitational potential as it like the initial position from the ground and the end position from the ground. That's it. So now enthalpy cycles, you have this enthalpy cycle. You can move from this. So in order for me to move from A B, this reactant, to C, I can move in this direction, and I can also move in this direction. These are two indirect routes, so there is no problem. So now in order for us let's take this example. So we have calculate the standard enthalpy change of the reaction this. And when you calculate the standard, they ask you to calculate the standard enthalpy change of this reaction. So the first step when you want to calculate the standard enthalpy change of a reaction is to visualize the values that have been given to you. The values that have been given to you are standard enthalpy change of formation. So you can form this standard enthalpy change of reaction by using the standard enthalpy change of formation. So you can see it from here. You see, you are going to use the different sodium ion. You have copper, you have this and that. When you add, you try to balance. If this first equation is balanced, when you add, you try to balance the next equation you have added. So here you are going to have delta H1, and here you are going to have delta H2. The standard enthalpy change of reaction is moving from left to right. Since the enthalpy change of reaction is moving from left to right, in order for me to move from this position to this position, I will move in this direction. So it's going to be negative delta H1 plus delta H2. So now you need to know that what in order to form from here, the delta H1 is actually the standard enthalpy change of formation of sodium carbonate times 2, because I initially told that in order for you to have these different calculation Hess's law, the first thing is to cram the definition. So when you memorize the definition, you have memorized that the standard enthalpy change of formation is actually what it is defined as the enthalpy or the heat absorbed or released enthalpy change when in order to produce 1 mole of a substance. You see that in this case you have instead 2 moles. Since you have 2 moles, you are going to multiply that 1 mole that was set in the standard enthalpy change of formation definition times 2. So for this delta H1 is going to be 2 times the standard enthalpy change of formation. You are going to have your answer. So this is a delta H1, and this delta H2, in order for me to move from here to here, I'm going to have so you have sodium carbonate and all that. You are going to have standard enthalpy change of formation of sodium carbonate. You are going to have standard enthalpy change of formation of carbon dioxide from here. I have standard enthalpy change of formation, but all of them are going to be 1 mole. Thus the energy are going to have all having a factor of 1 in front. So when you are going to do that, you are going to say now the total answer is going to be minus 2 of this energy plus all this energy in order to have the enthalpy of reaction. So you are going to have minus this plus all the other energy, and when you have all plus all the other energy, you are going to have your answer. So this is how you calculate. You can move you see that the direction in order to move from this here to here, you are going to take the opposite of this one. So that's why is you have a minus here, and you have the same direction of this one. So here you are going to have a plus, and that's going to give you a delta H of reaction. So that's how to calculate standard enthalpy change. So now the next one are the bond energies and the enthalpy enthalpy change. So bond breaking, we need to know that what there are different energy inside a bond. So that's why you have bond energy. Bond energy, the amount of energy needed to break a specific covalent bond is called the bond dissociation energy. So the amount of energy required to break a specific covalent bond is called the bond dissociation energy. We sometimes call it the bond energy or the bond enthalpy. The symbol for bond energy is given as E. We put the term bond broken in brackets after the symbol. So that's what you have to take in mind. So now example, now let's say that you want to calculate the bond energy in each of the bonds of carbon to hydrogen bond, carbon hydrogen bond. If you want to calculate all the bonds, so you need to know that what in order to calculate all the bonds, you need to break down all this. But this is actually delta H of the reaction. Delta H of the reaction, in order to calculate the energy in each bond, you need to know that in order to break down this methane, you are going to apply energy and break each of the bonds. But there are 4 bonds inside methane, so you say that this total energy delta H is actually 4 times the energy of each of the bonds. So in order for me to have this my final answer, I'm going to say that my final answer, that which is the bond energy term of carbon to hydrogen, carbon hydrogen bond, is actually equals to delta H divided by 4. That's the first step. My next step now is now in order to find for delta H. How do I find for delta H? I know that in order to find for delta H, I'm going to move from this to this. So I'm going to use the opposite of delta HF, and I'm going to use this in the same direction. So now I know that the value, in an easy way to find this energy, is via using their enthalpy change of formation. So I'll use carbon here plus hydrogen. When I move from here to here, I'm going to have a delta H of formation of methane, and from here to here, I'm going to have delta H of formation. So here is inside, because this graphite is solid and this is hydrogen, hydrogen here in gas. So it's going to be actually the enthalpy of atomization. So you are going to have one time the enthalpy of atomization. I initially define enthalpy change of atomization as the energy required to produce 1 mole of the substance. Since the energy required to produce 1 mole of the substance, here you have 1 mole, because here is going to produce 1 mole of carbon, and here is going to be 4 moles because it produces 4 mole of hydrogen. So that's the point. So when you have it, the delta H of the reaction in this case is going to be negative this, because in moving this opposite, you are moving the opposite direction to this in order to arrive this. So it's negative delta H of formation of methane plus delta H of atomization of graphite plus again 4 times delta H of atomization of hydrogen. So these are the different points which are involved in this chapter, and from me I say thanks for your kind attention, and please don't forget to like and subscribe for this channel. Thank you.